I want you to have some sort of a visual geometric understanding of differential equations and solutions to differential equations. And the best way to do that, I think, is to deal with what are called slope fields. A slope field for a first order differential equation is really just a way of indicating kind of graphically what that differential is saying about any curves that might solve it. Here we have a differential equation, y prime equals x minus y. This equation is a first order equation, and it's of the form where it's y prime equals some function of x and y. What this means is that for every pair of values, x and y, there is a y prime value associated with that pair. That means that every point in space, in xy space, is associated with a particular slope. And since a slope is sort of a geometric thing, right, you can draw a little line segment associated with each slope, then it turns out that you can actually create a very visual way of representing this differential equation. If we go about trying to actually display what the slope field is for this equation, then what we're going to want to do is we're going to want to actually draw in little slope elements for all of the points that are in space. Now we can't actually do this for all of the points in space. So instead what we've got here are what are called the lattice points. They're the locations where you have integer x and integer y values. And we're going to use these as just a way of getting an idea of what the broader slope field would look like. So for this particular equation, we have y prime equals x minus y. All right, so when we have y prime equals 0, then we're actually going to have a slope of 0, because that's what y prime is. So when x is equal to y, then x minus y will be equal to 0, and y prime will be equal to 0. And so what we can do is we can say on the line x equals y, which goes up like this, okay, we can actually create little line segments of slope 0, that is to say that they are horizontal on that line. Great. This, by the way, is called a method of isoclines or nullcline. What we just drew is a nullcline. Okay, these are locations that all have the same slope. Okay, so what we could also do is we could go through different slopes. We could say, all right, when will y prime be equal to 1? Y prime will be equal to 1 when x is 1 more than y. That will happen here on the line y equals x minus 1. So we end up with, we'll have a slope of 1 there, and there, and there, and there. Interestingly, this isocline that I'm putting in actually also has a slope of 1, and it's supposed to represent the slope of 1. What that means is that, in fact, this equation, or this curve that we just displayed, is a solution to this differential equation. So we end up with that y equals x minus 1 solves the differential equation. You could check it if you'd like. All right, so what we end up with here is we've got where y prime is 1. Now we need where y prime is negative 1. Y prime will be negative 1 when y is 1 more than x. That will happen here. So I draw in all my little negative 1 slopes, okay? And then we can just go ahead with more extreme ones. For every step that I take diagonally from here and down, okay, I'm going to end up increasing my slope by 1. So here I'm going to have a slope of 2. That's a little bit steeper than the slope of 1. And then slope 3 is steeper still. And then slope 4 is steeper still. 5, 6, 7, right? I can't necessarily tell exactly what the slope is based on the way that I'm drawing. I'm just doing my best to try to get what this is going to look like. And for every uh, point I go diagonally from here upwards, my slope is going to become steeper, but also keep in mind it's already negative. So we're going to end up with, here we'll have a slope of -2, then -3, -4, -5. All right, let's actually consider what this slope field is saying. What it's saying is that for any solution to this differential equation, and remember what a solution is, it's got to be something which, when substituted into the differential equation, actually makes the statement true. So for any solution to this differential equation, if it's going to pass through the line y equals x, then when it passes through the line y equals x, it must have this slope of 0. In fact, whenever it's passing through any one of these isoclines, it must have the slope that is necessary for that particular isocline, which means that we can actually get a pretty good idea of what the solutions look like. And there are many of them. So we can see that solutions that are over here are going to end up kind of moving upwards. They're following this slope. And so they're going to end up approaching this curve that's here. These will also. Every time we do this, we can get a picture of what these solutions are going to be doing, even if we don't actually know what the equations for these solutions are. So down below that line, we're going to get solutions that do this, okay? And up above that line, we're going to get solutions which let's say I have to make sure that they have a slope of 0 when they're passing through this isocline. And then as they go through it, they're going to turn around and start following those negative slopes. Okay? And so these are what the solutions to this differential equation are going to look like. Now, later in this class, you're going to be able to take this differential equation and solve it using one of a couple different methods. There's the method of integrating factors, and there's the method of constant coefficients. And I'm not going to present those to you at the moment. I'm just going to tell you what the actual solution is for the moment. So in general, the solution to this differential equation looks like this. We've got c e to the minus x plus x minus 1. Okay. Now you'll notice that this actually has this parameter c in it. That ultimately is coming from an integration. That's like the plus c that you were, that you lost points for on your quizzes last year. Okay? Don't worry, we all did. So that c is actually giving you the choice between which of these solution curves you want. Different values of c will choose different ones of these curves. You'll notice that when c is 0, we get x minus 1, which is the one linear solution to this differential equation. So what I would like to do is I want to actually show you using far better graphing skills than I have what this C is actually doing. And I want to show you sort of visually using a computer that this solution actually describes all of these behaviors. So here we are in a graphing calculator-like program. This one is GeoGebra. What I have here is the slope field for the differential equation we were just looking at, y prime equals x minus y. you'll notice that the computer draws a much better slope field than I do. And actually, it has the ability to become as fine or as coarse of an approximation as we want. But what I really want to do here is I want to demonstrate for you that it's the value of c in this solution, c e to the minus x plus x minus 1, that actually determines which of these curves you're going to get. So the way I'm going to do that is I'm just going to let c go ahead and change. Okay, and you'll notice that for different values of c, every single one of these curves is obeying that slope field, right? Every time that we're passing through one of those elements, it's doing so in such a way where it has that slope at that moment. Now I've modified the GeoGebra set that I'm working with, and I've added this point. Okay, this point is guaranteed to be on that solution curve. And as I move the point around, the solution curve will actually change depending on where the point is. Okay, what I really want to convey to you right now is that through every single point in space, there is a solution. And what's really important is that you understand that there's only one solution. Okay, and so no matter what, we should end up with a unique solution if we already know one of the points that is actually on the solution curve.